So that's the title. And here's the main points of this presentation about language faculty science. Its object of inquiry is the language faculty, and its method of inquiry is the basic scientific method, which I'll go over in a few slides. And these two determine the core properties of the following: hypotheses and predictions in language faculty science. That is to say, what kind of hypotheses do we entertain? What kind of concepts, theoretical concepts, can we use in formulating our hypotheses? And what kind of predictions are we making and testing? And what kind of experiments do we conduct? And how are we going to try to replicate the results of an experiment? That's basically the main points. Now, this is a preliminary empirical observation. So if you look at 1A, which is a Japanese sentence corresponding to something like every engineer praised his robot. すべての技師がそいつのロボットを褒めた. And the B and C is slightly different word orders, but the crucial elements of すべての技師 is there and そいつ is there. And the observation is this: intuitions about the availability of for each of the engineers, there's a different robot in question, his or her own robot. That interpretation, the possibility of that interpretation for sentences in one are not the same among different speakers. And they may not even remain constant even within the same speaker at different times, especially for 1B and 1C. The judgments seem to be affected by what's chosen in each of the boxes below, among other lexical, structural, and pragmatic factors. So you see soitsu in red in this box. There are other choices. So if you plug in other choices, judgments may be affected by that. Likewise, in this purple font, if we plug in some other things, such as 3人の学生 or 3人以上の学生, the things change or could change. Those are preliminary empirical observations, which may be useful to have before we start. That's why it's here. Now, again, the summary of the presentation is this. I will be presenting and talking about what we call a correlational methodology for language faculty science. And oftentimes I write LFS. One, hypotheses are in terms of a theoretical concept of C command. A C command is, what do I say, directly defined based on merge, which is a hypothesized computational operation of the language faculty. The postulation of merge is in line with the methodological minimalism of the basic scientific method, which I'll come to. Second point, predictions are about an individual's intuitions, about the relation between linguistic signs, sounds, and meaning. This is also in line with the methodological minimalism. Experiments and replication, therefore, are also about individual, within the same linguistic community and beyond. The basic scientific method demands that our predictions and our experimental results be definite. What makes it possible to pursue the basic scientific method in language faculty science is focus on definite correlations of judgments. That's the summary. Now, this is language faculties. Starting assumption, our starting understanding is that language faculty is something in our mind brain that is responsible for our ability to relate linguistic sounds, signs, and meaning. Therefore, it follows that hypotheses and predictions in language faculty science must be about what underlies that ability, directly or indirectly, right? What I call basic scientific method is this. Guess, compute, compare part, which is based on Feynman's guess, compute, compare. And I placed a PowerPoint file in the Dropbox folder mentioned in the workshop announcement. And so you see video clips and some remarks about that. Guess, compute. Well, that's basically deduce a definite and testable prediction from hypotheses. Compare. Obtain definite experimental results and compare them with definite and testable predictions. What? This is kind of funny. Compare with the definite and testable. I want to fix this. Definite. Oh yeah. Okay. Okay. I was okay. Sorry. Delete what I said about. Okay. Third point. Methodological minimalism. This includes hypotheses must be stated in terms of the minimal number of theoretical concepts. I say this includes because it essentially talks about when you make moves in your research, your moves want to be as minimal as possible. So it's not just about the number of theoretical concepts that we want to use. Lastly, replication. Experimental results must be replicable. Now, I call this basic scientific method for the reason that I assume anybody who is interested in finding out about anything in a testable and robust way will follow this. That's why I call this basic scientific method. And essentially, this is exactly what the Feynman mentions, although he doesn't talk about methodological minimalism, because that's matter of course. He didn't talk about replication because that's a matter of course. Oh, I forgot to mention something. I prepared something that too bad. This is slide 7. The initial part of slide 7 is from Chomsky's The Galilean Challenge essay. So he talks about Galilean challenge. Essentially, the infinite creativity of the language faculty is the Galilean challenge. And that, Chomsky reasons, leads us to postulate the existence of the computational system. Otherwise, we wouldn't be able to create or give rise to infinite creativity. Once you accept the existence of the computational system, given the methodological minimalism, you want to come up with the simplest possible computational operation. Taking two items and forming one, that kind of operation is the simplest possible computational operation that leads to the digital infinity in question, and that's called merge. Now we define a particular theoretical concept called C command based on merge, as defined in something C command something else, if and only if the first item is merged with something that contains Y. In a little box, I say we leave open until the choice has an empirical consequence, whether the containment relation above can be reflexive. That's not important. So the adoption of the concept of C command we get by reasoning in this minimalistic way. Once you accept or start out with the thinking of there is this infinite creativity, digital infinity, that leads us to postulate some kind of a computational system. And the simplest possible computational operation is some operation that takes two things, forms one. Based on that, we can now define this particular concept called a C command. According to Chomsky's general hypothesis, the basis for meaning is a purely hierarchical representation, where only the structural relations among its elements are encoded and not any other relationship. For example, linear precedence. That applies to any I language of any speaker, roughly speaking, in any language. In accordance with this view, we expect to be able to detect and replicate C command effects on meaning in any I language of any speaker, roughly in any language. We therefore formulate our hypothesis in terms of C command, using no other theoretical concepts, and try to obtain and replicate definite experimental results precisely in line with the predictions. So we look for a meaning relation pertaining to two linguistic expressions X and Y, which we abbreviate as meaning relation MR, X and Y, along with specific choices for X and Y, such that the possibility and the impossibility of the meaning relation MR can be taken as an indication of the presence of the absence of the C-command relation between the two items at a purely hierarchical representation. So from here, at the bottom, I say we formulate our hypotheses in terms of C-command. Up above, I mentioned something about we expect to be able to detect and replicate C-command effects. So that's the starting point of this research program. And for that purpose, we look for a meaning relation. What kind of a meaning relation gives us this? If C command, okay. Without C command, impossible. That kind of a meaning relation is what we look for. Once identified for a given speaker at a given time, such meaning relation holding between X and Y, two linguistic expressions, with the specific choices for X and Y, can be a crucial part of our experimental device for detecting C command effects. And such an experimental device, once established, can be used for exploration of various properties of the language faculty by the basic scientific method. So we start out with device for detecting C command effects. Once that's been done to a pretty good extent, then we can use that to explore other properties of the language faculty by the same basic scientific method. That's the general line of research that language faculty science is pursuing. Examples MRXY. I mentioned this once already. すべての技師がそいつのロボットを褒めた。For each of the engineers, there's a different robot in question. That is his or her own robot. Under that interpretation, and we abbreviate that as BVA すべての技師そいつ。The meaning relation BVA すべての技師そいつ can be used for the detection of C command effects only if its availability is contingent upon すべての技師 every engineer C commanding そいつ that guy in purely hierarchical representation. Little footnote here, I think. Oh no, footnote is, footnote shows up later. To avoid possible effects of the presence relation, such as すべての技師 preceding そいつ on the availability of BVA そいつの技師そいつ、すべての技師そいつ I'm sorry. We focus on sentences in which すべての技師 does not precede そいつ as in this. Now we see 1B and 1C. In both sentences, そいつ appears before すべての技師. We have an I language particular hypothesis about whether given two linguistic expressions X and Y in a phonetic sequence, whether X C commands Y in purely hierarchical representations. For example, Oh, here, that's the footnote there. When I say X commands Y, that's a simplification of something like abstract object corresponding to X, C commands abstract object corresponding to Y. And abstract object meaning object in the purely structural representation. And that's the abbreviation, but we can for now suppress that particular detail. With this simplification, NP1 ga NP2 CM being O marking or ni marking. So NP1 ga NP2 O or ni verb must correspond to this structure. And NP2 CM, NP1 ga, so NP2 O, NP1 ga, or NP2 ni, NP1 ga verb can correspond to this same structure in purely hierarchical representation. That's an example of a language particular hypothesis. The tree here is meant to be a 3D structure. So I'd like you to try to think about NP1 and the VP. They may be the precedence, just the hierarchical representation matters. They're kind of hanging around, moving around. Okay? But it's since I haven't been able to locate or haven't been able to come up with the 3D image of this, I'm still using this 2D image. Now, this is what counts as detection of C-command effects with respect to BVA, すべての疑似素。If a speaker rejects 1B and accepts 1A under BVA, すべての疑似素, that counts as the detection of C-command effects. 1B is a ga or structure. So if you map the phonetic sequence of 1B to a structure, you see, as in the tree structure, little tree structure on this slide, すべての疑似 is NP2. Soitsu is inside NP1, Soitsu no robot ga. We see then すべての疑似 does not see command Soitsu, 1B. Hence, we say if a speaker rejects 1B. What about 1C? 1C has an O ga order. The hypothesis that we just talked about says this 1C can correspond to a structure where すべての疑似 C command Soitsu, because of the hypothesis that we have here. So if a speaker rejects 1B and accepts 1A under the BVA interpretation in question, that counts as the detection of C-command effects. And also it counts as evidence for the validity of the hypothesis in 2. Because it's the combination of the hypothesis in 2 and something else giving us this effect. As it turns out, however, that there are non-structural language specific factors connected to particular lexical items, among other things, that can allow, Daniel, I should have a comma here, no?
Yes, it's a parenthetical.
Among other things, that can allow MR, for example, BVA interpretation in question, to be accepted in the absence of the proper C-command relation. And this is something that I mention in relation to this. Oh, now I can, okay, that's okay. I'm not gonna go back. The slide is coming up. The choice of X and that of Y, choice of Y for BVXY, among other factors, can result in different judgments among speakers and even within the same speaker at different times. Fortunately for us, these non-structural effects appear to be relatively stable across different MRs, allowing for us to diagnose their presence or absence via non-circular tests. Different MR here, we call a DR. Essentially, DR すべての義肢3つのロボット is the interpretation where we are talking about for each of the engineers, there's a different set of 3 robots in question. In the case of what we call a COREF, あの義肢そいつ essentially it means あの義肢 that engineer and そいつ him or that guy refer to the same individual. And we talked about this, we started up with this, right? As I mentioned earlier, depending upon what choices we have, such as すべての versus these other things, and many more options are there. And for the right-hand box, そいつ、そこ、その男、その義肢, and many more options. Intuitions about the availability of BVA XY, now DR XY prime, and COREF X prime Y seem to be affected by what's chosen in each of the boxes below, among other lexical, structural, and pragmatic factors. Now, in chapter 1 of the Mouton volume, I will be reviewing Hoji 1985 and some other book manuscripts and the book in 2015, going over all sorts of instances of BVA, DR, and COREF. And what has happened is that despite whatever efforts that author of Hoji 1985 was making, things were not as clear-cut as one may want to wish. So the judgments on BVA, as I mentioned here, can be affected by the choices of X and Y. And likewise, the choices of X in DR affects the judgments, and choices of Y, as in Soitsu, for example, affects the judgments on COREF. As I mentioned, what counts as Siekerman detection with MRXY, meaning relation between X and Y, is a combination of the following 2 things. 1, I can accept MRXY, that judgment, when by our hypothesis, X does not Siekerman Y. And I can accept MRXY when by our hypothesis, X Siekermans Y. The combination of these 2 constitutes Siekerman detection with MRXY. Here's a speaker. Now, because of our emphasis on individuals, remember, language faculty is internal to an individual. So we have hypotheses about an individual. We conduct an experiment on individual. So we have an individual there. And if the speaker detects Siekerman effects with particular choices of X and Y, those choices of X and Y for MRXY are good items to use for the detection of Siekerman effects for this speaker at that point in time. This detection of Siekerman effects, however, is not accompanied by rigorous testability. We can keep on checking. If this is not what happens, then we can keep on checking various other choices of X and Y until we detect Siekerman effects with the right choices of X and Y. So the detection of Siekerman effects depicted on this slide alone, that alone is not based on testability. You just keep on looking. You just keep on checking all these choices, and until you get, oh, now I get it, then you get the detection, all right, but without any testability. in a rigorous testability, you can't disconfirm anything. In order to make a prediction about the availability of MRXY testable, we got to be able to determine independently of MRXY whether particular choices for X and Y are good for the detection of Sigma effects based on MRXY for a given speaker at a given time. We try to determine that. We try to determine that by considering two other MRs, and MR1 XY prime, MR2 X prime Y. The former shares X with MRXY. The latter shares Y with MRXY. For example, BVA XY, DR XY prime, COREF X prime Y. We'll, for the time being, continue to illustrate the methodology for by using MRXY, MR1, MR2 instead of BVA, DR, COREF to emphasize the general correlational approach being pursued here. Again, here's the speaker. If the speaker detects Sigma effects with a particular choice of X, now we have MRXY prime. With a particular choice of X, this speaker detects Sigma effects. Then that choice of X is a good choice for the detection of Sigma effects for this speaker at that point in time. Crucial assumption at this point, the choice of Y prime of MR1 XY prime does not affect the availability of MR1 XY prime. Next, MR2. If the speaker detects Sigma effects with a particular choice of Y for MR2 X prime Y, that's a good choice of Y, for the detection of Sigma effects for that speaker at that point in time. Again, here, a crucial assumption at this point is that the choice of X prime of MR2 X prime Y does not affect the availability of MR2 X prime Y. When neither X nor Y is good item to use, this is what happens. The speaker is outside two circles. If X is a good item to use, but not Y, then the speaker is in the MR1 circle, so to speak, but not inside MR2 circle. That's our way of visually representing the compatibility between a particular speaker and the use of a particular lexical item, right? This situation is where Y is a good item for Sigma detection, but X is not. And finally, if X and Y are both good items to use, then we visually present the situation like this. And when you have this situation where both X and Y, both choices for X and Y are good items to use for Sigma detection, then we have found out based on MR1 XY prime and MR2 X prime Y that the particular choices of X and Y that are good item to use for Sigma detection for this speaker at this particular point in time. We can then use those choices of X and Y for Sigma detection for this speaker based on MRXY. Unlike the earlier situations, we now make a definite prediction about this speaker. MRXY is impossible for a phonetic sequence for which there cannot be a purely hierarchical representation where X sigmas Y. That's the definite prediction we now make because of the identification of good X and good Y based on DR the MR1 test and MR2 test. This is a definite and rigorously testable prediction, which corresponds to the star schema-based prediction in Hoji 2015, my Cambridge book. MRXY is not predicted to be impossible for a phonetic sequence for which there can be a purely hierarchical representation where X sequence Y. And that corresponds to the star schema-based prediction in Hoji 2015. Daniel, how much time do I have left?
You have about 20 minutes.
Okay, thank you. Oh, that's me now. That's researcher. Okay, that's me. Suppose I get sigma detection. Remember, sigma detection obtains when sentences or a set of sentences for which there is no C command between X and Y, let's say Y prime in this case, they're no good. With C command, okay. That's C command detection. Right? So now this is me, and suppose I get a C command detection with MR1 X Y prime. Suppose I also get C command detection with MR2 X prime Y. Furthermore, oh yeah, so I'm there, right? I'm in the intersection. And furthermore, suppose I get a sigma detection with MRXY. That counts as sigma detection with MRXY with rigorous testability. Remember, sigma detection based on MR1 only, MR2 only, or even MRXY without prior identification of which X is good, which Y is good. Those are sigma detection instances without rigorous testability. But now we've got identification. The particular choice of X has been identified with MR1. Particular choice of Y has been identified based on MR2 as good items to use for sigma detection. Therefore, now I have a testable prediction about MRXY. And then, because the third dot says I get sigma detection with MRXY, so I did get the sigma detection in a testable fashion. How is this to be replicated? How do we replicate this experimental results in my self-experiment? Well, the basic form of replication in the self-experiment is like this. I can use other choices X and Y and see what happens. If I belong to this intersection with given choices for X and given choices for X and Y that give us sigma effect, then I should be able to get the sigma detection with those newly discovered, newly identified choices of X and Y. I can do that. I can also check other sentence patterns beyond ga or ga, something like that. Check lots of other things, more complicated sentence patterns. But crucially, there should be of two crucial types. One is the type where C command is there. The other is the type where C command is absent by hypothesis. What about replication in non-self experiment? I want to replicate my results in other people's mind as well. With a speaker in the same linguistic community as the researcher, as myself, essentially I'm talking about speakers of Japanese. I want to see if this happens. This is what happens if we identify first good choice of X, good choice of Y, then you check MRXY. I also want to replicate this with a speaker of an I language substantially different from my own, essentially like speakers of another language. Same thing should happen. we identify a good item for X and good item for Y based on MR1 and MR2, and then we make a prediction for MRXY. Remember, X is shared between MR1 and MR. Y is shared between MR2 and MR, right? There are, with various choices for X and Y, we first try to identify the choices of X and Y that lead to detection of Seekerman effects with MR1 and MR2 for a given speaker at a given time. So if you have, okay, I can go on. We then check and see if we obtain Seekerman detection with MRXY with the same choices of X and Y. This applies to any type of experiment, regardless of whether it is a self-experiment or a non-self experiment. And of course, non-self experiment comes in two types, right? For me, Japanese speaker non-self experiment and non-Japanese speaker non-self experiment. And whether the replication is in relation to a speaker, I said the same thing. Okay, so I skipped this. When you have this situation, what we're going to do is we check other choices for X and other choices for Y, hoping that some other choices lead to Seekerman detection for this speaker for MR1 and MR2. If this is what happens, then of course we check other choices of Y, right? X is okay. X is working with this for this person. So in this particular case, we check other choices for Y and see if we obtain Seekerman detection with other choices for X. Now other choices of Y, I'm sorry. Now this one, we check other choices of X for MR1. Once we get to this point, we check and see if this speaker detects Seekerman effects with MRXY. Now I want to turn to self-experiment versus non-self-experiment issues. Researcher knows what's meant by MR, MR1, MR2, etc. I know what I mean by this meaning relation, but non-researchers do not. They have to be told in some way what meaning relation is being considered between two linguistic expressions. The experiment takes place in this way. Non-research, non-self-experiment takes place in this way, more or less. So you ask, is this sentence acceptable under blah, 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 right? And the judgment comes, okay, not sure, etc. The thing is, we must make sure in some way that the non-researcher understands that what the question mentions as the crucial meaning relation is indeed the MRXY that we intend. This relates to the issue. If you have ever worked on experiments dealing with meaning relations of this type, then you have the experience of how difficult it is. Oftentimes, it can be very difficult to articulate exactly how to present the intended interpretation, intended meaning relation to the experiment participant. You got to explain, is this acceptable under blah, blah, blah. Now, under blah, 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 depending upon how you say things change. And that's exactly why in my 2015 book, I spent quite a bit of space talking about exactly how we presented the sentence. So not only did I gloss sentences for the crucial sentences in the experiment and translated that into English, I also glossed sentences used in the instructions, so to speak, under such and such interpretation, because that matters You can't just say, we gave the instructions meaning this without giving Japanese sentences, then we don't quite know what the informant or participants got. So that gives rise to the need for sub-experiments. For example, sub-experiment on DR, that's every boy, 3 girls or something like that. Sub-experiment on DR can check whether a participant clearly understands how we convey the intended DR interpretation by checking whether or not they clearly reject the DR interpretation in B. In contrast to A, B, every teacher praised those 3 students. For each teacher, there is a different set of 3 students. A, every teacher praised 3 students. So in our sub-experiment on DR, sentences like this are included, and then we make sure that the participant understands what is meant by our instructions when we say under such and such interpretation. Now here's a non-researcher. Do they clearly understand what's meant by BVA-XY and or DR-XY prime, given the way we've specified the intended interpretations for DR and BVA interpretations? If yes, they are in the sub-circle, like that. So, oops, okay, now I gotta move on to this. So this person was here, right? Now we see if this person got detection based on DR. If yes, then this person is here. If no, then this person remains here, right? This person passed the sub-experiment test, but didn't have the detection with DR. Of course, if this person fails to pass the sub-experiment test, of course, this person is outside, right? This could happen when the person fails to pass the sub-experiment test, but seemingly giving us detection based on DR. But it's not very reliable because this person failed the sub-test. So we now see that if somebody belongs outside DR circle, no detection with DR, detection with DR, remember, this detection is not based on testable, it's not based on rigorous testability. If this person is inside, detection, outside, not detection. But then this and this are very different situations.
10 minutes.
Yes?
You have 10
yes.
minutes.
Oh, 10 minutes. Let me see. Okay. Thanks. And COREF, the same thing, right? Detection, maybe here or there. This detection is less reliable than this detection. Without detection. But this person is more reliable than this person, though. So this other slide I can skip. And now, if this person is in the intersection, we make the following rigorously testable prediction about this person. With the same choices of X and Y as identified through the DR experiment and COREF experiment, the speaker consistently rejects, the prediction is, the speaker consistently rejects sentences with BVXY if, by our hypothesis, no purely hierarchical representation corresponds to it, in which X C commands Y, no C command. That's the rigorously testable prediction. If the same speaker accepts sentences with BVXY, where C command is there, now we have a C command detection with BVXY, with rigorous testability. This is suppressed in this presentation, so I skip. And I talked about this, I-language particular hypothesis. Ga, o, for example, if I take CM to be o, ga, o, must, and o, ga, can correspond to a purely hierarchical representation in which NP1 asymmetrically commands NP2. We had this other hypothesis. If X and Y are good item to use for the detection of C-command effects at a given time, then BVXY is possible only if X C-commands Y. I'm abbreviating, simplifying things, but that's the way things are. We also need hypotheses about parsing strategy for the parsing of a given phonetic sequence. All right, PS is phonetic sequence as an NP, along with lexical specification that are needed for the category specification such as the verb and the noun. Based on the, okay, so now I want to talk about this. This is a Venn diagram based presentation of experimental results in the QDI 2017 spring. Sub-experiment DR detection, CoRef detection. So if somebody is inside the middle circle without C command, no good for BVA. Green means that's the way things are, plus they even accepted cases where C command is there. This is the same thing. And you see 180 people, about, I forgot, it's something like 80 or so people are outside subs. This sub-experiment is the something like 3人の学生, intended to be interpreted as narrow scope taker. Okay? And people who accepted those 3 students being a narrow scope taker, so to speak, then they're outside. People are outside DR circle if they don't detect C command effects with a particular choice of X. People are outside CoRef circle if they don't detect C command effect with a particular choice of Y. So out of 180, 9 people are in the intersection here, and everybody got detection. Nobody gave judgments based that contradict our prediction. Now, let me finish this one first. In the QDI experiment, there were 6 options for X and 2 options for Y. In every possible combination of X and Y, no one in the middle intersection accepted BVXY when, by hypothesis, X does not C command Y. And most in the middle intersection accepted it when, by hypothesis, X C commands Y. This, therefore, provides a strong empirical experimental evidence for C command effects on meaning, and hence for the existence of the computational system of the language faculty, as suggested by Chomsky in his essay, The Galilean Challenge, for example. This is replication of the definite correlational result of my self-experiment. The result of the experiment in English also replicates the definite correlational result of my self-experiment. Now, going back to this, remember I was saying, if somebody is outside DR circle, that doesn't necessarily mean the person is no good. Just the particular choice of X was probably not good. So we check other choices for X. In this case, other choices for Y. And if people are outside the sub-circle, then we want to see, okay, let's just see, we're gonna have a follow-up session and try to make sure that they understand what is meant, what we meant when we ask under such and such interpretation. So we expect more and more people are in this circle, and depending upon which choice of X, some people may be inside. Depending upon what choice of Y, some people may be inside. As I mentioned here, only 6 options for X and 2 options for Y in QDI experiment. So that's 14 graphs we have. But suppose we have 20 X's, 20 choices of X, like my own self-experiment, more than that. Suppose I have more than 10 Y's here. Then we are talking about 200 possibilities, which means we have 200 Venn diagrams. In each Venn diagram, we look at the middle intersection. And there shouldn't be anybody in the middle intersection who accepts BVA with the choice of X and Y in question when X does not circumvent Y. So if you only look at this, you see 180 people, which shrinks to 9. That doesn't look very good, some people may say. But actually, if you look at 20 X's and 10 Y's and look at 200 choice combinations, we have 200 Venn diagrams, 200 cases of intersection. Then surely we expect to have quite a bit more here, especially if you do follow-up session, making sure that they understand they belong inside the sub-circle here. 5 more minutes, Daniel?
More like 1.
Okay. Summary, good. We focus on individuals. This combined with the possibility that non-circumvent factors can affect our linguistic judgments leads to the recognition of the critical importance of the self-experiment by the researcher. One of the main purposes of an experiment, self or non-self, has to do with the identification of various options, including the options for X and Y that seem effective for circumvent detection for a given speaker at a given time. It's only based on such identification that we can design and conduct an experiment to test our definite and categorical predictions. It is the focus on correlations of judgments that makes it possible for us to pursue the basic scientific method, deducing, obtaining, and replicating predicted experimental results of a speaker of a language in any speaker of any other language. What we would do, if possible, with a speaker who ends up outside the center circle in a non-self experiment is essentially we check other choices of X and other choices of Y and see what happens, right? This applies to, non-self experiment is kind of strange. Okay. There's a error here, but I'm going to fix it later. And if a given speaker is outside the sub-experiment circle, well, then we try to conduct follow-up session and try to make sure that they understand what we mean. And we can, of course, conduct further experiments dealing with a number of additional sentence patterns, including scrambling sentences, multiple scrambling, long-distance scrambling, double object construction, spec binding, and so-called ergative NIGA sentence pattern, or so-called local disjointness effects context. Focus on definite and categorical correlations of judgments, as outlined, has yielded striking results. I don't have the time to go over that, informing us about the validity of various hypotheses put forth in the literature about such constructions. We can also deal with MRs different from BVA, DIAC, or Ref. I don't have the time to go over that either. C-command-based proposals in relation to ellipsis can also be examined by this method. But pursuit of rigorous testability when dealing with ellipsis requires a great deal of additional work methodological and experimental, especially when we turn to non-self experiments. I want to conclude by noting this. One, the viability of the proposed methodology can be enhanced if we can deduce the effects of our hypotheses from more fundamental hypotheses, such as Ga or Varv ought to be this, or Ga Varv can be this. Where do they come from? If such theoretical deduction receives experimental support by the proposed methodology for language faculty science or by its more advanced version, okay, so okay, fine. Two, given that the language faculty is part of the mind brain, it's natural for us to explore whether and how the categorical experimental results in language faculty science that we have obtained can be grounded and replicated in neuroscience, and what technological innovation might be needed in order for that to happen. And we'd like to make use of the C-command detecting device consisting of MR, MR1, MR2, etc. At a given time, evaluate structure-related hypotheses that have been put forth regarding Japanese. And something like this I'm going to try to do in chapter 1 of the Mouton volume in relation to my own work. In fact, we can try to evaluate any structure-related proposal by this method, as long as the proposal in question is stated in terms of C-command. What's noteworthy in this connection is that whatever device one come up with, whatever choice of MR, whatever choices of X and Y, okay, at a given time for this purpose is effective for that person at that time. And there is in principle no guarantee that the same device is effective for others or even for this person at a different time. It is through pursuit of correlations judgments that we can obtain and replicate definite and categorical experimental results. And that's what makes it possible for us to expect to replicate an experimental result of an individual such as myself in an experiment dealing with any other speaker of any other language. Maybe we can stop here. Maybe we